Hanging wire on there. We had to count how many loops. We ended up figuring that out other ways as well later on. We had to glue that. This is University of Wisconsin-Madison's rotating wall. We actually have it mounted in there. We ended up not doing that. And again, the finished product. This is the, you don't see the outer capacitor, but I later on cut out the two inner aluminum rings and then just had the outer two aluminum rings for the outer capacitor right on that styrofoam. This is the inner capacitor, the aluminum, and it worked. It held charge. Voltmeter. This is a diagram of our, just the solenoid on the capacitor, and the voltmeter measuring, voltmeter would be connected to these wires here, but if it was the outer capacitor, it would be connected with it. The power supply had to be connected to slip rings that ran through a pipe through there, and so we could feed power to the solenoid. It was the only way to get power to the solenoid. We didn't see what we were expecting to see if we never rotated. So we'll be seeing like a voltage climb when I turned it on. You'll see that really big charge, it would discharge a lot slower than that. So the initial spike, I think, will needs the changing the magnetic field, I think. I don't see much here. Should have been dropped down below, nothing there. This is positive 0.1 16 volts up there, e to the -3. This is one of these. This is an outer capacitor. So for the outer capacitor, Tate's experiment would work because he was experiencing a change in charge, and for a solenoid, change in charge should appear on the outside of the solenoid. So this is the found prediction for rotating magnetic field. This is Tate's method in his equation. So actually, we predicted something even larger for rotating magnetic field, but Tate's equation, he predicted something much smaller, actually. This is asking for both Tate's theory and ours. I believe Tate's theory had more to do with change in charge of the electron. Again, a whole lot of results from that as well. You can see it turned on here, but it almost looks exactly the same. Okay, I'm just going to go through this real fast. We have Purcell and the electric field. Okay, this is Purcell's electric field. It looks a little different. This is the actual field for a single charge. And this one conserves flux. Because you can be integrated, you get Q per epsilon naught. And when integrating in a sphere, around the charge. So regardless of velocity, so the velocity term just completely disappears. In his book, he derives the electric field based on experimental verification of conservation of charge in all frames. So charge, when the electrons change velocities inside the atom, it should retain charge. Otherwise, we get blasted or shock. So then, some of the behavior I want to point out of the electric field. The electric field seems to point at a previous location of the charge after it receives an impulse. So there's a light speed limit to information transfer. So you can imagine these kinks is traveling out at the speed of light. And so then you follow the line at once the previous location. You receive an impulse at some later time. Speed of light times dt would be a distance, radius. So also I in this case, I'm going to do this myself. For a current loop, it's different. So that's pretty interesting. The electric field pancake. And illustrate electric flux in 3 dimensions. That's important. And it's always perpendicular to the velocity. Yeah, and this this relativistic increase in the electric field is the same, I believe, is V cross B term. You can actually account for that. So the velocity with respect to the magnetic field of the charge, you can take into account relativistic effects. So you can just take the electric field of the charge plus these relativistic effects. The reason why the electric field doesn't rotate is important because here's one charge changing direction. Change direction by about 45 degrees and emits light everywhere. And that's not really realistic for an electric charge. Like I said earlier, this is actually realistic. It takes into account emission of radiation when the charge emits perpendicular, most of the light is perpendicular to the acceleration of the charge. And it emits no light in front and back. There is some relativistic effects though due to pancaking that I'm not taking into account there. And it's likely that since the electric field can't rotate, if you see any videos online of the charges going around in a circle, you won't see the electric field lines rotating with the charge as the charge goes around in a circle and creates light. Okay, so then we get an electric field pancaking. We have charge density increase. So basically, Purcell points out that you should see this change in charge density, but he doesn't really get into, from what I can tell in his book, what happens when you get a complete loop. And so this is like a charge, it has velocity, you're standing still with respect to the wire. The current accelerates. Important to know. Purcell said that the charge length, as the current accelerates, doesn't become more dense. And one of the reasons I think that is due to pancaking. So imagine you have a loop, and you have pancaking all around. But you don't have any difference in electric pancaking effects. So there's no reason for the charge to redistribute itself around the loop. So you could have current accelerate around the loop, but why would it change in charge density? There's no reason for it to, unless you're moving with respect to it. And we'll get into that. And this is where I got his charge, looked at his charge density equations, and I noticed that it looked like you could almost put a dot product in there. And this is your velocity, and then there's the current velocity. So here's you're moving, right? This charge is moving with you. This is moving faster in time. This charge is moving against you. It's moving slower in time. Well, this is less pancaked now. Right? This is more pancaked. And then, so basically, if it's more pancaked, then the charges can come in closer together, so you got a larger charge density over here, negative charges, and less over here. So it's, but over here, gives you too much charge density change. So, this is a parallel to this. These guys were doing, this is a paper by Constantine and Vivo, and they were looking at polarized light. And it hit me, it struck me. I realized looking at the paper, I was like, oh my goodness. They had a rotating wheel, and they were showing a rotating wheel with respect to relativity, and they observed we're moving, the time slows down more over here because they have a higher, larger relative velocity with respect to this part of the wheel than they do this part. You can think of this as the negative charges. So the negative charges are going to bunch up, you know, over here, and not over here. And then these are the positive charges. They're not rotating, right? So then you just pancake the whole wheel here, then overlap the wheel. Negative charges over top of positive charges, right? And you get more positive charge over here and more negative charge over here. And you get back to electric field. So that's what I modeled in FEM 4.0, and I distributed the charge around the loop by Q sine theta. So you just distribute that charge around the loop, but you're conserving charge. And you get your 1 over r cubed dependence as you're out here, because it's like a dipole electric field, but you're actually dealing with the 1 over r cubed dependence over the magnetic field, which is velocity dependent and direction dependent. So here's this red line down here. It's like you, the observer. And if you're anywhere along this line and you have a velocity with respect, it looks like the solenoid is moving with respect to you. That's what's really going on because you're in your own frame, you're stationary. Then it looks like the solenoid becomes like a dipole electric field. You see this electric field coming off. Now there's more to this than this because there's also electric field tilting. Marcel gets into that. It's not necessarily for me to get into it too much, but this explains why the magnetic field doesn't rotate, because if you start rotating this in the lab frame and you're observing the dipole electric field, then that means that if you're in the lab frame and this thing's rotating around in a circle, then you're moving faster with respect to these charges than you are these charges. And the charges are actually bunching up on one side of the solenoid. But if you're looking at something rotating in a circle, you can't say any of these particles are moving faster with respect to you than the other particles are. So there's no reason for there to be redistribution of charge. So it's assigning you, with the lab frame observer sitting in your own room with this solenoid rotating, a relative velocity with respect to the center of that current, which doesn't make a whole lot of sense. Okay, charge. Okay, let's see here. Magnetic field isn't due to a change in charge, so then the electric field is inside is due to a long solenoid. Basically, a change in charge for the long solenoid all happens on the outside of it. That's where you observe the electric field. But for a long solenoid, the magnetic field resides on the inside, mostly. That's where the strong magnetic field is. That's the dipole electric field right there. So it's not a change in charge, it's actually just a redistribution of charge along the solenoid, so it's all over here, and observing the dipole electric field. Conclusions I got from paralleling Purcell's electric field with the magnetic field is that the magnetic field not rotating defines relative velocity with respect to the center of the current. So it's a definition of basically relative velocity, and yeah, I just said, okay, then a rotating magnetic field implies a lab frame observer has to be given a relative velocity that varies with distance. So the farther you are from the solenoid, the greater your velocity is with respect to the whole solenoid. That's what a rotating magnetic field implies. So it's kind of odd. Doesn't make a lot of sense. And this is rather a disturbing concept and is likely not realistic. Conclusions. Experimental data suggests the magnetic field doesn't rotate. Theoretically, the magnetic field is likely to not rotate actually because charge redistribution. The velocity in the lab frame is realistic, and the electric field of charge does not rotate with the charge direction, it appears. Magnetic field defines the relativistic electric field of the charge, and it also seems to imply that a charge magnetic field would also not rotate. So it appears like the author that it is also like magnetic field radiates rather than rotates. And I think this is, you can parallel this to pulsars, rotating magnet stars, and also the equivalence to just the three-phase coils and rotating magnetic fields that way. Radial induction more so than rotational induction with rotating magnetic fields. Okay, I'd like to acknowledge some acknowledgements.
Yay for your wife.
Yeah.
I have more acknowledgements on here. Steve Monger, included you, Dr. Rapsel, Dr. Rapchek, Dr. Boy, and Dr. Pauly, and Dr. Brian Davies, and the physics department, all the students and the staff at the University of Wisconsin. It's a great educational environment. University of Wisconsin as well. Clay and Gilbert Spring, Doug Dillon. Okay, Carlos Paz Sullivan, he was the one who was working on the rotational wall. He gave us some good. I'd like to thank my partners in the project that were with me and were added to Ezra Skate at the time, and Jeff Carlson, and Brian Emerson, and Chris Frazier for a short time as a friend of mine too. And Mohammed Ashmi, that's the name of our on a trip up there, that was kind of fun. rest of my IW students, professors, and staff. Okay. Any questions? Sorry, it took a little longer than I wanted.
Does anybody have any questions? So you talked about radiation. So from the rotating solenoid. So you said that in the relativistic reference frame, the solenoid, if it's rotating, well, sorry, if it's not rotating. So that's how you use Purcell's theory to think about how somebody in the moving reference frame would see a solenoid. They would see a charge distribution, and that would be equivalent to magnetic field for somebody who's not moving with respect to the solenoid.
Well, somebody who's not moving with respect to a solenoid observes no electric field.
Right.
And so all they observe, the only way that they can observe the magnetic field is to use a magnetic field meter. The magnetic field meter uses moving charges. And so it has to use something in the inertial frame to actually measure, because it just doesn't exist in that frame at all, it seems like. So it's mostly in the relative frame is what the impression I get that it exists. But there is real energy in it, and that's an interesting, an interesting part as well. And the higher your velocity, of course, the bigger the electric field you start to observe. Is that enough to answer your question?
So this picture here is the solenoid is not rotating.
Oh, no. This one is not rotating.
But you're looking at it as though the solenoid is moving to the left at some high velocity.
Yes.
Right.
You, the observer, are moving with respect to it, but it's also moving with respect to you. And this is the intense. Notice the nice constant electric field on the inside. That's due to the nice constant magnetic field on the inside, regardless of your position inside. You get the rapid decrease on the outside. Now this isn't the complete picture. We're missing something else to this. If you're approaching this, the electric field should actually be pointing up. And that's due to another important, at least important, is electric field tilting. Now you have to actually include this. So if you're moving towards a current that's moving perpendicular to your direction. So this current these are the negative charges, I believe. Yeah, I think so. You're moving up, and you're moving towards the current. That current now has velocity towards you and up. So it has a diagonal velocity. But the positive charges are just sitting still with respect to you, but you're moving towards them. So now the positive charges only have velocity towards you, and that's it. You start pancaking their fields, and it's just up and down. They're pretty much pancaked. But over here, these guys, they got like a tilted electric field. You take that into account, these are negative charges, and the electric field is actually pointing up. And that has to be added on to this effect. You got dipole electric fields and you got electric field tilted going on all at the same time. I mean, that only, most of the effects, if you're closer to the wires and you're approaching the actual solenoid itself. If you're moving perpendicular, not so much. If you're moving with the charges, I should say. But if you're approaching the charges, then you start seeing electric field tilting.
I have a very simple question. I'm trying to understand why they should bring in relativity, whereas the motions involved are not relativistic, right? Even though you have thousands of RPM, it's still not relativistic.
Well, that's fascinating. The magnetic field is actually one of the few areas where we can actually observe relativity on a very small velocity basis, I guess I should say. There's so many charges in a wire, and just a small amount of time slowing down on one side compared to the other, just that small amount of charge when we observe these forces of the magnetic field.
So I've got a simple question for you. As a result of your experiment, would you consider that the way the introductory physics is usually presented, and how we present electromagnetic induction, is still on firm footing, or there's something we're currently presenting wrong that should be done different based on this research? Or does this research show we've been doing it right? You follow what I'm saying?
Now I have to think back to all I learned.
Well, that was the idea of the question. That's always my type of question.
And I really enjoyed learning about the relativistic parallels of the electric field and magnetism, and that opened my mind a lot, because when I began to understand that the magnetic field, you could use them, just the normal electric fields, and then you have the magnetic field, but that's the same as taking into account relativistic effects on the electric field. And I began, but honestly, what I learned is building blocks. I mean, you got me started, and so I'd have to say that what I learned was, I believe, correct. I don't know if I was ever taught that the magnetic field rotated or not, so that's just trying to answer that question.
So the interesting question, is in the Lorentz force law, there's the B cross B term, the force. So one way to think about if the magnetic field rotates is that what does that velocity represent? Whether it represents the motion of an actual charge, or is it the relative velocity? If you could think of the field lines as being able to move through space, could you think of that as a relative velocity with even just a still charge and those lines moving through? And it seems as though, based on his research and just sort of studying the problem with people, that you can't, that velocity is in that reference frame if the charge is moving with respect to the B field in that reference frame. So you can't assign that velocity to the field itself.
So that velocity is always associated with the charge on its frame, not really any kind of relative to the field velocity. So in other words, it would seem that that's the way it's usually presented in our introductory physics anyway, right?
That's right.
We don't really talk about the field moving. So we haven't really.
No, we didn't break it. We didn't break any new ground.
Yeah. Well, no, I don't think that's the point. The point is, though, that you verified that the way we're presenting it is the correct way of thinking about it, which I think is important.
Sure.
Because it seems these other two experiments that Dustin reviewed very thoroughly in his thesis, you did a good job of that. It seems to me that they left it so open-ended, right? And that what you were basically trying to do was close any doubt there.
There's no experiment completely closes.
No, I understand that, but each experiment should leave the out hole smaller.
I really had my questions after not observing a rotating magnetic field, because I thought, you rotate the magnetic field rotates, it should rotate, right? And that really got me thinking, and then I really wanted to look into all the theoretical ideas behind it. Why didn't I see it what I was expecting? And inspired. Another thing was, something important. I just wanted to reiterate what the effect of the rotating magnetic field indicated. So we have a B field out here, right? It's coming down, and it has a velocity, right? So then it's moving, right? So then what you do is you give yourself a velocity. And the reverse of this is that you see yourself as moving, especially when you put this way. So then the solenoid will appear to be moving this direction. This is for a rotating magnetic field. And so then this charge, and we figure out, okay, electron for electrons. So then electrons, we do a negative current I, and we move this way, around the loop. So we have up here and in up here, and it's rotating. So, what is this? Okay, so then, and this whole cylinder has a velocity, so then over here, with respect to you, so then I guess, so then you're moving this way, electrons are moving this way with you, so then this should be more positive over here, this should be more negative here. But that's only because these electrons are moving faster with you with respect to that was really what got me. I was like, there's no way that magnetic field can rotate because it's saying that it's being given a velocity with respect to the entire current. And then creating a dipole.
So what is your current position?
I had applications everywhere, and they snagged me and pulled me off.
This is in Washington State?
Washington State,
That's a community college.
It's a community college.
And you're the physics lab person?
Yeah, well, I set up the experiments for them, and I maintain my chemistry back there, keep all, safety, and,
So you do physics and chem?
yeah. I have to say, physics has come in handy even in chemistry, so.
There wouldn't be chemistry without physics.
So this magnetic field not rotating, that brings up an interesting question. If you think about the sun spots are essentially created because there is differential rotation in different areas, different surface regions on the sun, they rotate at different speeds. And so the stuff that's causing the magnetic field is relative rotation, and that's why you get this, you get the loops coming out from the sun's surface, and you get the sunspots. So how does that relate with magnetic field not rotating here?
It's a good question. In fact, somebody else we talked to brought that up as well. And I was believing, what is it? It's like you guys, but you do see the sun, you see these these kind of magnetic loops that are coming out, and they do appear to be rotating. I was thinking that, again, it's the parallel to that radial induction, which parallels to angular induction. So there should be a way of thinking about that. And so what was it I was doing? I was like, you feel currently here. So they do follow the magnetic field lines. And what is that? It's like, well, one thing was we can again use that three-phase coil, and we can make what looks like a rotating magnetic field, even though nothing's rotating. It can be pointing this way, and then later on it can be pointing up.
So it's just an optical illusion.
Yeah, I think pretty much. But I mean, no, if you hold the current though, I mean, if something's passing through it, it's definitely there in that direction.
I think also the key thing, right, for your experiment is that you're doing it in free space, or charge-free space, but the sun is not charge-free space. So the magnetic field is being done with the plasma, with the charges. So it's the matter and the fields interacting, and the fields follow the matter as the matter moves around. And that's whereas we don't have that. We have a plasma anywhere. We shouldn't. Anywhere outside of the coils.
This is an interesting question I pondered. I tried to wrap my mind around that because when I did this on the sun, does look like it's rotating, but then again, so does this. But then I feel you could say really does kind of rotate in a way, but information, like if you look at the magnet, right? And you have magnetic field lines way out here. And then you have some that are closer to the gallery.